Hi everybody, welcome back to our discussion about light and matter in our astronomy series. In the last video we discussed how the different types of spectral features arise in stars or other objects that emit radiation and why the Kirchhoff's rules are as they are. In the video before that we discussed blackbody radiation and how blackbody radiation can be used to determine the temperatures of stars. In this video, we're going to analyze other features of spectra, in particular the Doppler shift and the Doppler effect, and what we can learn from spectra that experience the Doppler effect. So first, if a source is moving toward an observer, the wave crests are going to be scrunched up. They're going to be observed to be closer together. One way of thinking of this is just imagine the source being at rest and you're moving toward the source. Well, so you hear, let's say it's a sound wave, you hear one wave crest, which gives you a certain experience in your ears, but by the time you hear the next wave crest, you've shifted yourself a little bit closer to the source. So the time between experiencing the wave crests has become less, and therefore you get the wave crests more often. So that would be a higher pitch of sound that you would experience. Whereas if you're moving away, you experience one wave crest, and then by the time the next wave crest reaches your ears, you're at a slightly farther distance, so it had to travel a little bit farther in order to reach your ears. That means that you're not getting the wave crests as often. We experience that in sound as a lower pitch. You have experienced this before. Whenever you have been on the road, when, say, an ambulance is coming toward you at high speed, you hear the pitch of the siren being noticeably higher, and then as it passes you, suddenly it switches to being lower. Same with a train going by. You hear the train going like, after it goes by you. So that is the Doppler shift. The same thing happens for light, and for the same reason. Because in physics, it's all about relative velocities. It's not about like whether it's one thing moving versus another thing moving. It's all about relative velocities. If the distance between the source and the receiver is increasing, then the waves are going to end up getting stretched out according to the receiver. If the distance between the source and receiver is getting shorter, then the waves are going to be scrunched up according to the receiver. So this can be seen in this diagram right here. According to an observer toward whom the source is moving, the waves get scrunched up because by the time the next wavefront is emitted, the source has moved. And the person on the opposite side sees the opposite thing. So those waves end up getting stretched out. And there also actually is a transverse Doppler effect as well when there's a 90-degree movement, but that's not something that needs to concern us for this discussion. So there's an equation for this. It's an important equation. It's an equation you should know. The equation is that the shift in wavelength compared with what it normally would be is equal to the speed of the relative speed of the source and observer divided by the speed of light. Now, this parameter, this delta lambda over lambda, is also known by another term. It's something that we're going to come back to later in the course, but I want to introduce it now. This delta lambda over lambda emitted, or lambda rest if you prefer, is often abbreviated by the symbol lowercase z for redshift. Now, those of you who have heard the term redshift might wonder, is like, well, wait a second, I've heard this term before, and they talk about galaxies experiencing a redshift of 5 or something like that. Does that mean they're going away from us 5 times faster than the speed of light, and Einstein was wrong, that things can't travel faster than the speed of light? So, it does not mean that, although things that are cosmological distances away from us can move away from us faster than the speed of light. It's just that they can't send signals toward us that would end up getting to us faster than the speed of light. In other words, we would not be able to observe those sources. What this means is that the formula is wrong. In other words, delta lambda over lambda emitted is not exactly equal to V over C. The true formula is that the right-hand side is equal to the square root of the entire quantity. You remember, ready for this? The square root of 1 plus V over C all over 1 minus V over C. And all of that is under the square root. That's the real formula. However, as long as the speed of the object or the source or their relative speeds to each other are significantly less than the speed of light, then it is valid to say that that square root function that I just gave you simplifies to being approximately v over c. So, as long as you're moving a small percentage of the speed of light, we can use this approximate formula. But as soon as you talk about large percentages of the speed of light, in other words, once your redshift gets over about 0.1 or so, in other words, once that wavelength shift gets more than about 10%, you should probably start using the real formula. Anyway, what does this mean? Well, here's an example. Let's consider an astronomer measuring an emission line from the spectrum of a galaxy. And based on the other emission lines in that galaxy and their relative strengths, the astronomer happens to know that this particular emission line was actually emitted with a wavelength of 676.5 nanometers, because that's the element it corresponds to. It emits that line at that strength at 676.5 nanometers. But it's been observed at 678.5 nanometers. So the question is, how fast is the galaxy moving relative to us in kilometers per second, and is the galaxy moving toward us or away from us? So first off, we can see that the galaxy is moving away from us. The wavelength is shifted toward longer wavelengths, which means that the relative speed between the galaxy and Earth is positive. If that relative speed is positive, that means that it must be going away from us. That's what a positive relative speed means. It means that the distance is increasing. If it was a negative relative speed, then the distance would be decreasing, and that would have been a negative shift. So, what is the shift? Well, the observed wavelength is 678.5 nanometers. The original wavelength was 676.5 nanometers, so the amount of the shift was 2 nanometers. So going back to the formula, the speed compared to the speed of light is equal to the amount of the shift divided by the original wavelength. So it'll be 2 nanometers divided by 676.5 nanometers. So we're going to plug that into our equation, multiply both sides by the speed of light to get v by itself. I already canceled the units of nanometers for us, just so that we don't have to see them. But they should be there, but they cancel, because 2 nanometers in the top, 676.5 nanometers in the bottom, they cancel. Speed of light in meters per second is 3 times 10 to the 8, but in kilometers per second, it's 3 times 10 to the 5th, and we were asked to express our answer in kilometers per second. So we get a speed of 887 kilometers per second. Why these units? Well, to some extent it's tradition, but in cosmology we will often discuss something called the Hubble constant, and the Hubble constant is expressed in units of kilometers per second per megaparsec. So, in fact, just introducing that now, this has a direct application to the Big Bang. The first evidence that the universe was expanding was actually found in the 19-teens, with the realization that all of these so-called spiral nebulae, with the exception of the closest, brightest ones, were all moving away from us. And then in the 1920s, Edwin Hubble was able to discern that there is a relationship between the distance these things were from us and the speed at which they're moving away from us. In fact, he used standard candles, in particular Cepheid variables, variable stars that they're named after the star Delta Cephei, which has a certain pattern in its brightness variations. It's one of the stars in the constellation Cepheus. And this calibration between the period of the brightness variations and the actual average brightness of the star, or of this type of star, this was calibrated by Henrietta Leavitt, who studied these types of stars in detail back in the 1900s and 19-teens. She observed a whole lot of these in the Large and Small Magellanic Clouds, and since those objects are quite distant from us, and since they're so distant, that means that pretty much most of the stuff that's in there can be assumed to be about the same distance from us, at least relatively speaking, then she was able to calibrate a period luminosity relationship. Well, Edwin Hubble used this period luminosity relationship and found these types of stars in the Andromeda Galaxy first and proved that the Andromeda Galaxy lies well outside of the Milky Way, as well as a few other galaxies. And then, when he started studying these in more detail, he found that there was a roughly directly proportional relationship between the speed at which the object was moving from us and the distance that the galaxy is from us. And here we're talking about distances of millions of light years to tens of millions of light years. Now, as we'll discuss in the cosmology unit, Edwin Hubble's original estimate for the expansion rate of the universe, in this case, was actually it was wrong by a factor of several, because it turns out there are multiple types of Cepheids, and he was actually looking at the brighter type, but he thought he was looking at the fainter type, making them closer, but he was actually looking at the brighter type, which means they're in truth farther away. So that mistake wasn't really completely overcome until the 1950s. But in any case, this discovery, by analyzing the spectral data of these galaxies and the degree to which the spectral lines shifted, was able to allow astronomers to discern that the universe itself is expanding. And upon analyzing this with Einstein's general theory of relativity, relativity actually has that possibility already taken into account, that if such a thing is to be discovered, then this would mean that the universe came into existence a finite amount of time ago, in an event that we now call the Big Bang. Now, this is just one of many applications of stellar spectra using the Doppler shift. Another includes the fact that a rotating star will have some parts moving toward us and other parts moving away from us, and by observing that star just by masking out different parts of the star, astronomers can determine the star's rotation rate. In addition, the widths of spectral lines, which the rotation rate will also influence, but the widths of spectral lines can also be influenced by the temperature of the star, as well as the variations in temperature across the surface. In addition, magnetic fields in the star will split the spectral lines into different parts, called the Zeeman effect, and that's something we're actually going to look at in Unit 7 when we start talking about the Sun. So there are lots of applications of analyzing stellar spectra, and in particular the Doppler effect. The Zeeman effect is not an example of the Doppler effect, but it's a magnetic effect, but nonetheless just analyzing these spectral features, these spectral lines. And in summary, just summarizing this entire set of these last 5 videos, including this, there are really 3 kinds of spectra, which come from either hot solids, compressed gases, diffuse gases, cold gases, etc. And even plasmas will give you different types of spectra. And continuous spectra, that is blackbody spectra, come from hot solids or compressed gases. And when you have something like that, you can determine the temperature of the solid or the compressed gas by fitting a blackbody curve to it, finding where the wavelength of peak intensity is, and fitting that into Wien's displacement law. Emission line spectra come from luminous, somewhat diffuse gases. Those might be in the atmospheres of hot stars. Those might be just in the interstellar medium, especially areas that have been ionized by hot stars. Absorption line spectra come from continuous spectra that have been passed through a cool gas. For example, maybe starlight passing through the atmosphere of a relatively cool star. As things go, our Sun can be thought of as a relatively cool star, at least compared with stars that have lots of emission spectra in their atmospheres. So, in this picture here, the star Sigma Orionis is a black body, but it's also hot enough that it's ionizing this whole area around it, giving emission spectra if you were to pass the light of this pink region through a spectrograph. And this dusty area, which makes up the Horsehead Nebula, and the area around it, if you were to look at the stars through here, you would see absorption spectra because of all the dust and gas in between us and the star. Why do these spectra occur? Because electrons orbit nuclei in discrete orbits for reasons that we already discussed in a previous video. And so hot gases will tend to have enough energy to, in their collisions, knock electrons to higher energy levels, from which they will spontaneously emit radiation of specific wavelengths, giving you emission spectra. And electrons that are orbiting atoms that are in cool gases will often more likely be in lower energy levels, because molecular and atomic collisions will not have been energetic enough to get them to higher energy levels, and thus they will be more likely to absorb radiation of specific wavelengths, hence giving you absorption spectra if you happen to be viewing something emitting blackbody radiation through such objects. So that takes us now to finally what we were just discussing in this video, the Doppler effect. Wavelengths of light will be shifted according to whether the object and the observer are either moving away from each other or toward each other. If they're moving toward each other, it's going to be a shift towards shorter wavelengths, what we like to call a blue shift, because if it starts like in the middle of the visible part of the spectrum, the shift will be more toward the blue end. If it starts in the middle and the source and receiver are moving away from each other, that shift will be more toward longer wavelengths, that is, more toward the red end of the visible spectrum, if the original spectral line was in the middle of the visible spectrum. So we call that redshift. So blue shift is when they're moving toward each other, redshift is when they're moving away from each other. The change in wavelength is proportional to the relative velocity divided by the speed of light, as long as that relative velocity is small compared with the speed of light. If it's not small, then you have to use the real formula. So that is the end of our discussion about light and matter. The next set of videos, also part of what I consider often to be the light and matter unit, will be about telescopes and observing instruments. So hope to see you all then, and thank you for watching.